Hello students. In example number 4, we're now going to look at something a little bit more involved compared to examples 1 to 3. Because of that, I'm also going to encourage you to make use of the benefits of these YouTube videos. Specifically, if you look along the bottom, probably somewhere near the bottom right corner of this YouTube video, you'll find a gear that looks something like this. If you click on it, you can both increase the screen size of this video, just in case you want to zoom in on something else, and increase the resolution of the video. You can put it up to 480p or even HD. Let's get to it. What we have with this example is a question that asks you to calculate the diameter and the height of water, that is the side water depth for a settling tank. Again, the diameter and the side water depth, the SWD, of a settling tank. You are told that the average flow rate of water through the settling tank is 15,000 gallons per day. You're also told that the detention time is 225 minutes. Finally, you're also informed that the overflow rate is 0.5 cubic meters per square meters per hour. Okay? If you look at this, you'll notice that this unit is actually a unit of speed. And it actually represents the speed at which, if the particles settle at a speed that's lower than this, they actually get flowed away from the settling tank. So if the particles settle at a speed that's slower than this, they will not settle to the bottom, they'll actually be dragged out of the tank. Okay, the formulas we're going to be using are these two, the detention time formula and the overflow rate formula. Okay, let's do it. In the interest of keeping this neat and tidy, I'm going to confine most of my work from here on. So the first thing that we're going to do is actually rearrange this formula to compute what the volume of water is going to be in this tank. Okay, let's do this. For this formula, we have the detention time, we have the flow rate. We can therefore calculate what the volume of water is in this tank. The volume of water, by rearranging this formula, is equal to the detention time times the average flow rate. At first glance, these units don't quite jive. We have minutes here for a time unit, and we have days here for a time unit. So we need to do something about that. So what I've done is this. By employing these conversions that I remember by heart, but that you can likely look up on your handy-dandy mobile devices, I'm converting days first to hours and then to minutes. And that's okay because this minutes and this minutes will cancel out. Now, in addition to that, I'm also going to be preemptive and recognize that the units I'm going to get out of this for volume is going to be in gallons. However, as an engineer, I prefer to work with units that have lengths to it when it comes to volumes. It just works out better. So I'm actually going to convert this gallons to cubic feet, which kind of makes sense. Gallons is imperial, feet is imperial. Now, I'm going to remind myself what the conversion from gallons to cubic feet is, which is 7.5 gallons is 1 cubic foot. Now, I remember that, but you can actually look it up if you're not sure. Ready? .39 cubic feet. Okay? All right, so we know what the volume of water is in here. Now we're going to employ the overflow rate to calculate actually what the surface area is, the cross-sectional area is of this tank. Ready? So I'm going to first rearrange this formula. Okay, I have the flow rate. I have the overflow rate. I'm going to rearrange it for this area as follows. So the numerator is 15,000 gallons per day. The denominator is 0.5 meters per hour. 0.5 meters per hour. And that's because this meter squared cancels out with this cube, right? So you'll be left with meters per hour. It's a speed. Okay? So now I have to do some manipulation with these units to get an answer that's in surface area units. Okay? So the first thing that I'm going to do is convert some of the units in the numerator, gallons. I'm going to convert them first from gallons to cubic feet, and then from cubic feet to cubic meters. Then I'm going to convert days from days to hours. And that's great, because then I'm going to end up with cubic meters, which is going to cancel out with meters to give me meters squared, and hours, which is going to cancel out with hours. Okay, and all I'm going to be left with is square meters. Now, if you're unsure about this step here, and I recognize that I've gone through this fairly quickly, don't hesitate to make an appointment with me, and I'll be more than glad to go over this with you. So the answer we get here is that the surface area of this water is 4.72 square meters. The next thing we need to do now is to calculate what the diameter is from this, right? If we know what the surface area is, we know that the area of a circle is pi d squared divided by 4, or pi r squared. We can solve for the diameter to get the value of the diameter. Ready? Okay. So that's what I'm showing right here. So that the value of the area is 2.45 meters per diameter. What about the height of water? What is the value of the side water depth? Well, we calculate that by using the value of the area and the value of the volume of water. Okay? So what I'm going to do is erase this so that I have a chance to show that in more detail. Okay, so remember this, the height of water is equal to the volume of water divided by the surface area, because it's a cylinder. The volume of water we found was 1.39 cubic feet. The surface area we found was 4.72 square meters. You notice how the units don't match? That means we either have to convert this from imperial to metric, or this from metric to imperial. It doesn't matter. But since I've already calculated the diameter to be in metric, I'm now going to convert this from imperial to metric, as follows. I remind myself that 1 foot is equal to 0.3048 meters. That means that this is true cubed as well. So that then, when I do this cube, this cubic foot and that cubic foot cancels out. We're left with cubic meters, which cancels out with that, to give us 0.0083 meters. So now we have the side water depth, we have the diameter of this tank, we're ready to conclude this exercise. And voila, I've made the final answer obvious and unmistakable. Now before we finish this example, we should have a look at whether or not these numbers make sense. Does the side water depth of such a small number, this is 8.3 millimeters, make sense? Well, the numbers say that it does, but doesn't make sense in real life. Would you have a settling tank that has only 8 millimeters of water in it? Well, as it turns out, that's only because I've given you such a low flow rate. 15,000 gallons per day is actually very, very little in terms of a water purification plant. Okay? So this is more meant to give you an idea of how to proceed with an example like this. And always question yourself whether or not the numbers at the end make sense.